Can you actually speak to that, the 30-hour session? I mean, this is not, from everything I know about computational geometry, doing this kind of thing from your perspective is not, that's not easy. That's, what is it? The uncertainty, the open questions involved, I mean, even just on the algorithm front, how to do that efficiently. And then plus the usual programming thing of debugging, like suffering through the trickiness of it. And we don't have really, at that time, you don't have the tooling to really visualize everything that's going on really well. And you probably like using some crappy editor. I mean, there's just a lot of like friction here. So the 30-hour session is one that's probably rough. It's a rough one.
Your brain works in different ways, and depending on your state, right?
Right.
There are some things that require really working on a problem fresh, where you've put together a bunch of logical pieces, and now you just need to write a whole lot of code to make it all work together, and you know, plumb a whole lot of data between a whole lot of different algorithms. But I think our brains have vastly more horsepower than we're able to directly access by thinking of what code to type next. And after you've been working for a very long time, you can get into a sleep-deprived state where you have much, much more direct access to that low-level knowledge.
That's great. Yeah.
Because there are symptoms that are well studied of sleep deprivation. One of them is short-term memory loss, and so you're working without like the easy recall of the code you just typed. But your brain is then freed to think about other problems, and I'd built up this intuition over a very long period of time. So the foundation for the subject is the binary space partitioning tree, this data structure invented by a computer science graphics researcher Bruce Naylor.
Mhm.
Carmack had picked up on that and had used the technique in Doom to really great effect. And I'd picked up on that, and Unreal Engine was using this technique for all of its graphics and rendering, but it was just additive geometry everywhere, and it had a lot of overlapping polygons and was pretty inefficient. So I had the idea that if we had a BSP tree, there was a really efficient way to do constructive solid geometry, and to do that, you had to break down the ways that different pieces of geometry can fit together. I broke it down into like 14 different cases, and most of them are pretty simple. Crank them out. Anyways, I got towards the end. There were some pretty complicated things like, what? How do you deal with coplanar polygons? They're in the same plane,
Yeah.
and pointing in the same direction versus the other direction. In what cases should you keep them? In what cases should you eliminate them? And so on and so on to create really efficient geometry output. And just plowing through it, eventually through mostly deduction, but some trial and error too. Like sometimes you just have to try the possibilities and see what works. I cranked it out and it worked. And the next day I came in like kind of weary and I was like, oh wow, this actually did work. It wasn't just a dream.
So you're considering the edge cases also. I mean, that's the problem with geometry is like there's probably just gonna be all kinds of weird polygons that you have to. So you're like thinking, you're imagining the edge cases and trying to see how do I not create inefficiencies in this algorithm while still considering the edge cases, allowing for the edge cases.
Yeah, it's pretty easy to write software that's like 99% correct. It's
Yeah.
the 1% that's the really hard part, and where the devil lies in the details.